When we map the internal wiring of a modern neural network, we consistently find a glaring anomaly. During processing, the model takes a massive amount of its computational weight and dumps it onto entirely uninformative, isolated tokens. Researchers call this the attention sink. It occurs across almost every major architecture. In large language models, this weight pools on the very first tokens of a prompt. In vision models, it gathers on blank background patches. In every case, the network is obsessing over useless data. This behavior creates severe operational bottlenecks. These massive attention dumps generate numerical outliers in the model's activations, making it difficult to compress models for consumer hardware. Researchers have also documented a consistent correlation between these sinks and higher rates of model hallucinations and decreased interpretability. The consistency of this behavior across different models suggests it is not a random glitch. It is a universal structural pattern wired into the foundation of modern AI. Because this issue touches so many domains, the research has been highly fragmented. Different labs have discovered disparate symptoms without a single theory to connect how the memory issues, the outliers, and the accuracy drops relate to one another. This survey paper is the first major effort to unify that landscape. Produced by a consortium from Tsinghua University, the University of Hong Kong, and industry teams like Meituan, it aggregates over 180 studies into a single cohesive framework. The authors organize the field into a specific taxonomy: fundamental utilization, mapping how we currently exploit sinks; mechanistic interpretation, detailing why they form; and strategic mitigation, outlining the engineering required to eliminate them. By following this roadmap, we can deconstruct the mathematical root of the attention sink and see the exact blueprints for the next generation of models. To solve the problem, we have to understand why the model creates a sink. The leading explanation is known as the softmax limitations and no-op theory. Look at the standard equation for self-attention. The softmax function enforces a rigid mathematical rule. The attention weights distributed across all tokens in a context must add up to exactly 1. This creates a problem during attention underload, when a model processes a query but finds no meaningful semantic match in the context. Because the softmax function is forced to reach a total of 1, it forcibly dumps the remaining probability mass onto a designated sink token, even if that token is irrelevant. To prevent this massive dump from corrupting its logic, the network learns a no-op mechanism. It suppresses the value vector of the sink token, pushing it towards 0. When the massive attention weight is multiplied by this near-zero value, it produces a minimal update, allowing the model to satisfy the math without breaking the calculation. Over millions of training steps, these pathways harden into outlier circuits. The sink tokens become stable geometric anchors, a designated wastebin for the model to store excess attention mass. The attention sink is a learned workaround. Because the transformer lacks a way to say none of the above, the network engineered its own escape hatch to satisfy a human-imposed mathematical rule. This realization leads to the first dimension of the research: fundamental utilization. How are engineers managing this behavior in live production environments today? A major problem occurs when we try to save memory during long conversations. Most models use a sliding window to forget older tokens. But if that window evicts the initial sink tokens, the subsequent queries lose their designated dump site. Without the sink, the attention weights scatter, and the model's output collapses into gibberish. The current industry standard is sink token preservation. As the memory cache fills up, the system permanently locks the first few tokens in place. The sliding window is then restricted to only overwrite newer blocks, keeping the sink available for every future query. Engineers identify these anchors by analyzing their geometry. Sink tokens reliably show a distinctly low cosine similarity when compared to the average key vector in a sequence. This mathematical signature allows preservation algorithms to target them with high precision. This approach allows for stable, ultra-long context windows, but it remains a form of symptom management. We are accommodating the limitation rather than fixing the underlying inefficiency. And that brings us to strategic mitigation. The engineering goal here is to architect a transformer that functions without needing attention sinks at all.
The primary structural solution identified in the survey is the gated attention mechanism. Instead of fighting the softmax rule, researchers install a new pathway. By adding a learnable gate directly into the attention block, the model can modulate the output down to 0 when no relevant information is found. It no longer needs to dump mass onto a sync token to satisfy the equation. This shift breaks the cycle of outlier formation. Because the network can genuinely do nothing when appropriate, the activations remain uniform and the attention sync phenomenon disappears entirely. The paper indicates this is more stable than alternative methods, such as modifying the softmax function with clipping. Clipping often flattens the distribution too much, making it harder for the model to maintain sharp focus on specific, highly relevant tokens. Moving from passive preservation to foundational mitigation represents the next step in making these architectures scalable. The taxonomy in this survey shows that mitigating the attention sink is a direct path towards solving several disparate deployment bottlenecks at once. First, it simplifies post-training quantization. By removing the massive activation outliers that attention sinks create, we can compress models into lower bit integers without the numerical errors that previously ruined performance. In multimodal models, this mitigation reduces hallucinations. When the attention mass is prevented from pooling on useless background patches and dynamically shifts back to semantically dense data nodes, the model is less likely to invent visual details that aren't there. It also addresses model security. Because sinks typically sit at static, predictable locations like the first token, they act as targets for adversarial attacks. Attackers can craft specific prefix triggers, malicious instructions that align with that focal point, to hijack the model's attention and force it to follow their commands. Resolving the attention sink results in immediate improvements to speed, memory usage, accuracy, and system robustness across different model types. The attention sink is a specific geometric adaptation. To satisfy the human-imposed softmax rule, the network learned to build its own internal waste bin to manage excess attention. The industry is now moving from passive strategies, like locking sync tokens in memory, to an architectural approach where attention is regulated by gates. Mastering the attention sink allows us to move beyond observing how transformers manage their limitations and towards designing models that function without them.